Okay, welcome. So let's continue working with the apply family of functions. And now the context where we want to use these functions is bootstrapping. And so we're going to create a function to construct a bootstrap distribution and come up with a bootstrap confidence interval that's going to use an apply function. And we have talked about several apply functions now. And so when we're using apply functions to create functions or using them in loops or in the context of other code, it is much, much safer to use lapply. So I highly recommend using lapply and not using sapply or vapply. And the reason is with sapply, it kind of guesses what the output, what the array is going to be to store the results. So sometimes sapply creates a matrix, sometimes a vector, sometimes a list, and it might not be clear what to expect. With sapply, that also is the situation with vapply. We don't know the structure of the output that's going to be returned. And so that's dangerous, particularly when we want to take that output and use it as input into another command. So generally what we do is we'll use lapply. We know that what comes out of lapply is a list. And if I want a matrix or a vector instead, I can convert that list into another data structure if that's the route I want to go. So in the code cell below that we're going to take a look at, we're going to use the lapply function to create a bootstrap distribution. And then we'll compare that as far as how efficiently that is to run compared to, say, a for loop. But here's how this command is going to work. So we're going to let B, capital B, denote the number of bootstrap resamples we're going to generate. So B standing for bootstrap here. So we're going to set as like a default, we're going to generate 10,000 bootstrap resamples. And then we're going to calculate a mean from each of those bootstrap samples. I'm going to store all of my bootstrap sample means in a vector that I called boot underscore stats. And how I'm going to calculate each entry of that vector is as follows. So I'm going to apply the lapply function, and the data that we're going to apply it to is the indices of the boot stats vector. It's actually going to be a list at first. So I'm going to have an index in boot stats that runs from 1 up to and including B. So this is just a vector of integers from 1 to 10,000, including those endpoints. Then with lapply, we need to indicate a function that we're going to apply to each element in X. So here's a function that we're going to apply to the number 1, we're going to apply to the number 2, and so on. So we're not going to actually use the values in the vector in our function beyond just corresponding to the index of where the value is being stored. And so we're going to define this function, and we're going to define what's called an anonymous function. So I could have defined this function separately in some other code and called it, my function, and defined it as function I, and entered my code, and then entered my function over here. But this would take up some computer memory. I need to store my function, and then in this command over here, it's going to read in that function. But I actually don't need to use this function anywhere else other than inside this lapply command. So I'm going to save a little bit of memory here by not creating this function, storing it elsewhere, and then calling it into this command over here. So I'm just going to create my function inside of the lapply function. So what this function is going to do is it's going to run this boot sample. It's going to create this boot sample using that same sample command we just talked about. So here's create bootstrap resample and then calculate the mean of that sample. And this is going to do it for all of the values 1 to 10,000. So it's going to create 10,000 bootstrap samples, calculate the mean of them, and then store them in this object called bootstats. But just recall, the output of lapply, the results of lapply are stored in a list. So here I ran this code. If you run this code, you'll get some different values because this is based on randomness and we haven't set the seed for this code cell. So every time I run this code, I'm going to get slightly different output. So you can see the randomness involved in this process. But what this is corresponding to is we picked a bootstrap resample, we calculated its mean, we picked another bootstrap resample, we calculated its mean, and they're all around 261, which was the mean of our original sample. But here you can see some level of variability, and then we can use that variability to build in some margin of error into our interval estimate. So this just created the list of bootstrap statistics. What's left to do afterwards would be to calculate quantiles that are going to give us the cutoffs for a bootstrap confidence interval. And just recall how we identify these cutoffs. So for example, if we were trying to find a 95% bootstrap confidence interval, then that means we want 95% of the area of this bootstrap samples in our interval in the middle. So that's what I'm indicating over here. The confidence level, for example, was 0.95. Then we can think about what is the value of alpha, which is the area that is not in the middle. So if we have 0.95 in the middle, that means we have 0.05 in each of the two tails, or in total in the two tails, and we want to split that evenly in each of the two tails. So we have one of the cutoffs is going to have an area of 0.025 to the left of it. So the lower cutoff of my bootstrap confidence interval is going to be, in the case of a 95% confidence interval, at the 0.025 quantile. And similarly, for the upper cutoff, we want an area of 0.025 above it to the right. So that means the area below that cutoff, in the case of a 95% confidence interval, would be the rest of the area, which is 0.975. So the upper cutoff is the 0.975 quantile. For other confidence intervals, we do a similar conversion where we take the confidence level, we identify how much area is outside of the middle by calculating alpha, which is 1 minus the confidence level, and then we split that missing area up evenly in the two tails. So the lower tail is going to be the alpha over 2 quantile. The upper tail is going to be the 1 minus alpha over 2 quantile. So that's what we're going to implement, and we'll do that in the next video.